In this video, I'd like to talk about the distributions of sample mean and sample proportion. And we need these two for building the interval estimates for population mean and population proportion. Related to this topic, we have Central Limit Theorem, which explains the shape of the distributions for sample mean and sample proportion when certain conditions are met. For example, when we have large sample for sample mean. We're going to talk about these as well. So in this chapter, we're going to be building interval estimates for population mean, mu, and population proportion, p. And in order to understand the formula that we're going to use later on, it's very important to understand the distributions and the shape of the distributions and the characteristics of the distributions of sample mean x bar and sample proportion p bar. So x bar, yes, so sample mean. For the example that we did in class, EAI, if this sample mean and sample proportion, since we're taking random samples, the sample that I take is different from the sample that another person takes. The sample that I take right now can be different from a sample that I take a few minutes later because these samples are random. Therefore, the average of the numbers, the average salaries of the sample that I take can be different from a sample to another sample. So that would make a random variable itself. The sample mean is itself a random variable. So we're taking samples of size 30, 500 times, 500 different samples of size 30, and we're recording the sample mean. But the difference here, I mean, if you look at the sample mean and compare it to the salary column that we had in EAI example, EAI employee example, you see that these numbers are much closer to each other. So that's one observation here. The second thing, the second column that we have here, again, if you take 500 random samples of size 30 and you find the proportion of people who took the training program, again, this sample proportion itself is a random variable. And if you, again, look at these sample proportions, you see that these numbers are much closer, much close to each other. I mean, we just have the sample, basically the population proportion as our benchmark to compare. This is not actually like this one, whereas we had for sample mean, we had the exact numbers for annual salary and we can compare. Anyway, if we just take these large numbers of samples and of a large enough sample of size 30, and we draw the distribution. We actually build a histogram for sample mean and sample proportion. For sample mean, as you can see here, this really looks like a bell-shaped distribution, a normal distribution. This is for X bar, right? X itself necessarily did not have a normal shape distribution. But more interestingly, for P bar, the values that we had for P bar, if you draw the distribution, if you draw the histogram for P bar, you're going to end up having actually a normal shape, a symmetric distribution, right? These are some observations that reinforce the central limit theorem, which again, like I said, explains a special condition that should be met in order to have normal shape distributions for X bar and P bar. So X bar, again, doesn't matter what type of distribution your actual X has, in this case, annual salary, X bar always has the expected value of X bar is population mean. And this is a very crucial characteristic for X bar, which makes it an unbiased estimator. And this is why we use X bar as the center of our interval estimate. So X bar is an unbiased estimator. The expected value of X bar is mu, and the standard deviation of X bar for an infinite population, for a large enough population, let's say more than 1,000 members in your population. If you have more than 1,000 members in your population, you can assume it's infinite population, and you can take this as the standard deviation of X bar. Standard deviation of X bar is the standard deviation of X divided by square root of n, sample size. And as you can see, as you increase the sample size, you expect the deviation in your X bar, sample mean, to decreases. So sample size increases, the standard deviation, the typical difference between the numbers that you take as your sample mean, that number, the typical difference, is going to decrease, right? Then, which means basically the sample means are going to get closer and closer to each other. And they get closer and closer to the mu, population mean, actually. We have, in cases when you have a small population, you have to consider a finite population correction factor, which you simply multiply this by the general standard deviation for population mean, which is sigma x divided by square root of n. In most examples, we're going to assume we are working with infinite population, so I'm not going to really focus on this. All right, but then, so that is what we just talked about. So I said standard deviation of X bar, sigma X bar, is sigma X divided by a square root of n, sample size. But then we do not have, most of the time, we do not have sigma X. So we have to estimate. We have to estimate. How do we estimate? We take the estimate for sigma, which is sample standard deviation. You remember stdev.s in Excel functions, stdev.s for sample, all right? So when you divide it by a square root of n, it gives you an estimate for sample, for the standard deviation of sample mean, all right? So central limit theorem now. So if we just focus on X bar, we just said the mean of X bar is mu. Standard deviation of X bar is standard deviation of X divided by square root of n. Now, but we did not talk about the distribution of X bar yet, the shape of the distribution of X bar. Central limit theorem starts to actually talk about the shape of the distribution and says whenever certain conditions are met, the shape of the distribution of X bar becomes closer and closer to a normal distribution, closer and closer to a normal distribution. For X bar, the condition is as follows: when the sample size is large enough. And this, in practice, we just consider a sample size of larger than 30 to be a large enough sample size for us to be able to assume that X bar is normally distributed. So when you have a sample size of 30 or larger than 30, you can take the implications and the result of central limit theorem for assuming that the sampling distribution of the sample mean X bar can be approximated by a normal distribution. with the mean of mu and a standard deviation of either sigma divided by sigma x divided by square root of n, or you can estimate it by s standard deviation of the sample divided by square root of n. So this will make our life much easier when it comes to interval estimate, and we'll see how later on in the next videos. But here I'd like to show you this example, which actually shows you the impact of sample size. Here you see when the sample sizes are 2, assume you take 500 samples of size 2, and when you draw the distribution, depending on the size of, depending on the shape of the actual variable. In our example, in EAI example, we had the salary. So assume if this was the distribution of X, numbers are uniformly distributed. When you take sample size of 2, you see that you will end up with a triangular. And as you increase sample size 30, the distributions become more and more symmetrical and close to a normal distribution. And this really is a very, very powerful tool, the central limit theorem, because doesn't matter what type of distribution you have for your X, for your annual salary in our example. Once you have a sample size of 30 or larger, X bar sample mean is going to have a normal shape distribution. And it's very important because we're going to actually use this feature for building the interval estimate. All right. So in this case, expected value of X bar is mu. So you can assume a normal distribution for X bar, sampling distribution of X bar, a normal distribution around the center of mu, which is in this case 51,800, and with a standard deviation of sigma divided by square root of n, sample size around like 730. So that is basically the sampling distribution that we were looking for, all right? And now, as you increase the sample size, so this black one is for the sample size of 30. If you increase the sample size to 100, you see that the graph becomes basically narrower. The standard deviation of the mean decreases. The center is the same, but the standard deviation decreases from 700 to 400. So the graph becomes taller, but narrower. It gets closer and closer to the center. So that is basically the implication of increasing the sample size. All right. Now, this was for the sample mean X bar. Let's now take a look at the sample proportion. Sample proportion is simply the proportion of the number of the frequency count of the interest, whatever it is, divided by the total size of the sample, right? The number of elements in the sample that possess the characteristics of interest. For example, the proportion of, if you're talking about the proportion of female students in class, you need to count the number of female students in class divided by the total number of students in class, all right? So P bar now has almost same, very, very similar features as X bar. Its P bar is an unbiased, again, estimator for population proportion, meaning that expected value of sample proportion is the same as population proportion. And again, we're going to focus on the infinite population most of the time. Standard deviation of P bar, standard deviation of P bar is going to be square root of P population proportion times 1 minus P population proportion divided by N sample size. So that would be the exact population standard deviation of P bar, all right? But again, we don't have this sigma and then we don't have P actually. So we have to estimate these sigma P bar by standard deviation of P bar by taking P bar instead of P in this formula. And if we do that, it's going to be sample standard deviation of P bar or standard deviation of P bar, estimated standard deviation for sample proportion is equals square root of sample proportion times 1 minus sample proportion divided by size of the sample, N. So that will give you the basically the standard deviation or estimated value for standard deviation of P bar. Again, so far we've been talking about the expected value, the center of the distribution, and we also we just defined the standard deviation. We haven't talked about the shape of the distribution. Again, central limit theorem comes to the picture and comes to our help. And here it says the condition that we have now is this. If you have a large enough sample size that if you multiply it by P or 1 minus P, whichever is smaller actually, and if the result is greater than or equal to 5, that means you have the conditions for central limit theorem, and you should be able to assume that you have a normal distribution for P bar. So again, sample size times P. So let's say if P is 0.3, sample size, so your sample size should be, I'm just gonna consider, let's say 0.5. If P is 0.5, then your sample size should be greater than or equal to 10. So this is basically the condition that has to be met in order for you to be able to assume a normal distribution.